Welcome back to Demystify Sci. I'm Shiloh.
I'm Nastya.
Today we have someone really special on the, well, we usually have special people on the podcast, but this idea that we are playing with today is something that's very close to our hearts. And it is the simple idea that interpretations are important and necessary in fundamental physics. And one interpretation that we've been very excited about and we've played with on the show before with Carver Mead is the transactional interpretation of quantum mechanics, which says that when we're looking at any phenomena involving electromagnetic radiation, we can't just think about the one atom that's emitting the light. We have to think about two atoms at play at all times. And today, to walk us through the inception of this idea, we have its originator, John Cramer. And he's had a really wild career spanning everything from working at CERN to writing science fiction books to developing the transactional, I almost said theory. It's not a theory. The transactional interpretation of quantum mechanics, where, of course, quantum mechanics is the theory that makes testable predictions, which is the hallmark of a theory in physics. The question is, what do those results actually mean? That's the interpretation.
And this is a topic, like Shiloh said, that we've played with on the show a lot, which is that you have really perplexing and paradoxical results in the quantum world. And when you have something that's really weird, you have two options. You can either say that it's really weird and borders on magical and mystical, or you can see something that's really weird and you can start to go deeper into the physical reality and try to piece together what are the actors involved that could be giving you the result which seems really weird but is actually based in something that's really quite ordinary. And so the transactional interpretation of quantum mechanics allows us to look at something like the really famous Freeman-Clauser experiment, where it appears that you can have entangled photons that violate Bell's inequality and reinterpret it as being a phenomenon that is A, physical, and B, transactional, which is to say that the system is not just a bunch of disparate parts that are just randomly interacting in a way that appears to be inconceivable in the realm of normal statistics or normal probability, but it is in fact an interconnected system. And so we go through all of the details of how the violation of Bell's inequality isn't really as weird as it seems. We go through the history of how Cramer developed the transactional interpretation of quantum mechanics. We go through the things that he's been working on since he stopped working on physics, and it's really a really wide-ranging conversation.
And I might just take a moment to plug our other YouTube channel if you want to check out more of our ideas about this, which is called Material Atomics here on YouTube. And we're actually working on our first book that kind of summarizes our ideas, but it's really similar to these ideas of transactional quantum mechanics in that there are two atoms involved. The only real difference as we see it is that instead of the second atom reaching backwards in time to interact with the first, it's already connected physically to its neighbor. And so it's interesting to me in looking at the work of Carver and of Cramer because they both have this idea that time reversal is necessary. But when we ask him on the show if it would be reasonable to just imagine the two being connected and both participating in the light event, he's kind of like, yeah, I guess so. And so, again, interpretations seem like they don't matter on their face, but they really do open up the possibility landscape for what comes next and what's developed technologically in the future. So I think that interpretations matter a lot more than we give them credit for, and they don't have a home in physics, and the philosophy department thinks that they're physics, but the physics department thinks they're philosophy, and there's nobody who's willing to really dig into this in the institutional setting. So it's a really cool blind spot that we think matters a lot and is going to matter a lot in the future. So anyways, check out our work at Material Atomics and look forward to our book, which will hopefully be coming out in the next year.
And if you like what we do and you want to support the show, come over to patreon.com/demystifysci We have a really amazing community of podcast listeners. We get together with them every Sunday at 10 o'clock Pacific time. And we talk sometimes about the podcast. Other times we talk about theories that people have run across in their explorations. And we're really trying to create a place that is a hangout. It's not just people that are listening to the podcast separate from one another, but there is a place where we can gather and we can really interact with each other and learn from each other and figure out how to have conversations on this larger scale. So it's kind of an experiment, but it's a really cool thing to participate in. So come on over if you have a little bit of cash to spare. If you don't have cash to spare, that is totally fine. I understand. You can like, comment, subscribe. You can share the podcast with your friends. You can recommend guests. And you can just tell everybody you know about the podcast. It's the best thing that you can do is help us spread the word, because you are the absolute key for us being able to grow, whether or not you have any money to help us out.
And growing, of course, means that we're going to get better and better guests on this show because everybody wants a bigger microphone to talk to. With that being said, we hope that you grow in this conversation as well. And we'll see you next time.
The scientific revolution starts now.
Let us see in the dark.
We have talked to a lot of people about quantum mechanics, but at the end of the day, the interpretations become difficult.
Yes.
Especially with things like entanglement experiments, but
Yes.
really even just the wave-particle duality kind of breaks people's brains at the end of the day. And so I wanted to just read a quick little bit from the paper that sets the stage for the problem.
Okay.
So this is a paper that you wrote with Carver Mead, who we've had on the show twice. He's a close friend of ours, close science friend, let's say. I think that's a fair way of putting it. You guys write, at the most basic level, a simple observation illustrates the central conceptual problem. An excited atom somewhere in the universe transfers all of its excitation energy to another single atom, independent of the presence of the vast number of alternative atoms that could have received all or part of the energy. And so this is kind of at the heart of things. Why is it that light has this, what we call quantized transaction that occurs? Why does all of the light go to one place versus all of the other places it could be?
You know, this is the dichotomy between classical mechanics, where the energy would be spread all over the universe, and quantum mechanics, where a single quantum of energy moves from one atom to another. And there's a deep mystery about how that can happen, because the energy ought to go everywhere. It shouldn't all be concentrated in the other atom. And the view of the transactional interpretation is that what's happening is there is a handshake process where the original atom sends out a signal called a retarded wave that goes everywhere, saying, "Hey, I have a quantum of energy I'm ready to transfer," and various possible receivers around the universe receive this and send back a reply, which is called an advanced wave, going backwards in time so that it arrives back at the original atom at the time of emission, saying, "Hey, I'm ready to receive this quantum of energy." And at that point, there has to be a selection process in which one of these acknowledgement signals that arrives is selected to be the one, and a signal is then sent back more directed to that one, and this happens back and forth until the energy is transferred. And that's the transactional view of what's going on, and it's consistent with if you think about things this way and you look at the mathematics of quantum mechanics, you can actually see this process in the mathematics of quantum mechanics to some extent, because quantum mechanics uses a symbol for the wave function, which is called the Greek letter psi, And if you look at almost any calculation, there will be an equal number of other symbols that say psi star. And what that means is that you take this mathematical function and you take which is complex. It has a real part and an imaginary part, and you reverse the sign of the imaginary part. You make that negative, which is called conjugation. And the result is that a wave function traveling forwards in time, if you take the complex conjugate of it, it moves backwards in time and carries negative energy into the past rather than positive energy into the future. And so the original atom sends out positive energy as an advanced wave. The responding atom sends back negative energy as I said it wrong. The original atom sends out a retarded wave, which carries positive energy. Negative energy is sent back to the original atom. The energy on one end goes up and the energy in the other end goes down until all the process is taken care of.
I mean, what I love about this, if I could I just add something, is that traditionally when we're taught about light in college and we're studying basic physics, it's not clear to us that there's two atoms necessarily involved. And it doesn't seem like that should be a radical idea, right?
Like the photon concept gives the sense that an atom is able to just shoot out this little bullet. And so if you have a single atom universe, then that atom would still be able to produce light. But it seems the transactional interpretation says that at minimum, you must have a two-atom universe in order for there to be light.
Yeah, if an atom isolated in the universe with nothing else there would not be able to lose any energy. It would be blocked. And there's some worry about neutrinos because it's very hard to absorb neutrinos. And I worried about this for a while, and then I came up with an explanation. But if you apply the same kind of quantum mechanics to neutrinos, it's hard to see. There are if you take an atom that does a process called beta decay and emits say a 1 million electron volt neutrino, the chances of that neutrino being absorbed between the now and the end of the universe is not very high because neutrinos are so hard to absorb. And so the question is, how can neutrinos be emitted if there's no absorber on the other end? And,
do you think about neutrinos as a kind of light?
Yeah, I mean this is a simplification. Neutrinos are complicated. They have a different spin and they probably have a mass, which is non-zero. Light photons have zero mass, rest mass, and neutrinos have a zero rest mass. We still don't know how big it is, but we can set limits on it. But if you treat the neutrino as a wave that has to be absorbed by a transactional process, that is a bit of a problem. My solution to it was that the advanced wave, that when you emit a retarded wave, you also emit an advanced wave at the same time. That's part of the process. And the advanced wave goes backwards in time. And what happens when it reaches the Big Bang, the end of the universe? It can't go any further than that. And an analogy with a transmission line where you have a pulse going down the transmission line and you put a short on the end that stops it, it makes a reflection that goes back the other way. And so the idea is that in a open-ended transaction like a neutrino, there's a reflection from the Big Bang that verifies the process so that you can have an open-ended emission that way.
Do people think
that was one of the original sort of worries about the transactional interpretation when I first conceived it? And I published a paper incorporating this sort of Big Bang reflection mechanism in order to justify it. It's sort of a detail, but it's something that people worry about.
Do people think that the neutrino has mass because of what's left over in that beta decay process between the starting ingredients and the end ingredients?
Because neutrino oscillations with neutrinos in the sun have been observed, and this implies that you have a massive particle. But it's a very small mass. It's certainly less than an electron volt, and probably less than a thousandth of an electron volt.
We've gotten very deep into the details very quickly. And so I like to always start these conversations with a 30,000-foot view of the topic. And so maybe before we circle back to neutrinos, we can actually look at the question of how does the transactional interpretation of quantum mechanics differ from the standard theory? What are the things that it does? How does it address problems that the standard interpretation cannot possibly deal with?
Yeah, let me say, first of all, that in spite of the fact that people like to talk about quantum mechanics as one theory, there are differences of opinion about the theory itself, embodied by Schrödinger and Heisenberg. From Heisenberg's point of view, this goes back to what do you mean by a wave function? What is a wave function actually telling you? It's a mathematical representation of the physical presence of a particle, but what is it telling you about that particle? From Heisenberg's point of view, particles are always point-like little objects that have almost zero extent. They're really tiny. And what the wave function tells you is the probability of finding that little point-like particle in various locations all over the place. From Schrödinger's point of view, the particle is not point-like at all. If the wave function is spread out over a certain distance, that means that pieces of the particle are spread out over the same distances. In other words, the wave function represents a distribution of the presence of the particle. The crunch comes because if you have charged particles that are point-like, say an electron, and it has nearly zero dimensions, the electric field as you go if you look at the electron closer and closer, the electric field as you go in and in and in and in gets bigger and bigger and bigger until it goes to infinity. And this is called the self-energy problem. And the self-energy problem is fundamental to the Heisenberg formulation. In extensions of the Heisenberg formulation, like quantum field theory and quantum electrodynamics, it causes infinities that have to be sort of subtracted by hand by a process called renormalization before you can go any further and do calculations. And there have been theoretical papers published showing that renormalization is sort of a kludge, and if we knew what the final theory of gravity and quantum mechanics neatly resolved was, it could not include renormalization. So renormalization is a fix for the problem, which is probably not really accurately describing what's going on. In the Schrödinger approach, where the particle is spread out over the whole wave function, there's no renormalization problem because there's no self-energy infinities involved. And and so in principle, that ought to be a killer that would move people away from the Heisenberg approach in the direction of the Schrödinger approach. Unfortunately, the Heisenberg approach has a very easy way of including spin and multidimensional effects in one thing or another. And the Schrödinger approach is sort of stuck in 3 dimensions plus time. And it's very hard you can put in spin by hand, sort of, but it's not really a very elegant way of doing it. So contemporary theorists prefer the Heisenberg approach, and most of the theoretical physics and particle and high energy physics has moved in the direction of quantum field theory and quantum electrodynamics, which have these self-energy problems, but they're ignored. In the 1950s, when I was a graduate student, my professor told me that the quantum electrodynamics had this self-energy problem, and it was ugly and it had to be subtracted in a really unphysical way. But this was just a temporary thing, and pretty soon they would figure out what was going on and have a better theory. That was in 1959 or something like that, and it's now 2024. And what the theorists have learned to do is sweep that under the rug and not pay any attention to it anymore.
Yeah, so I think perhaps a simple way of putting the the difference here. I can just quote from your
Yeah,
paper.
I didn't answer your question, but what I was getting at was that the Carver and I prefer the Schrödinger approach, and we have sort of removed a roadblock that was preventing people from moving much further in the Schrödinger approach. Namely, the Schrödinger approach did not have a way of dealing adequately with Einstein-Podolsky-Rosen experiments and non-locality. And we found the fix for that, a way of adding explicit non-locality to the Schrödinger approach. And so that paper that you read is our first attempt to do that properly.
Before we move on from this, I want to understand a little bit more about the infinities inherent in the Heisenberg approach. You say that as you go deeper and deeper into the electron potential, the energy rises to infinity. Do you have a physical interpretation of that, or do you think that that's just...
The physical interpretation of it is that it doesn't allow you to do any calculations, so it's not any good, so we subtract it away and then we proceed to do calculations. That's the way it's dealt with.
And is this akin to the...
Like I said, it's been sort of swept under the rug. In fact, some people, if you look in the literature, some people claim renormalization is a wonderful thing and that made a virtue instead of a vice out of it. But from my point of view, it's something that should have killed the theory a long time ago. The other problem with quantum electrodynamics is that if you try to use it to calculate the energy, the intrinsic energy of the universe, what's called the cosmological constant, you get a really embarrassment. You get an answer which was 10 to the 56 times too large to match what's presently going on in our universe. And in any normal situation, if you had a theory that was wrong by a factor of 10 to the 56, you'd throw it in the garbage can. But they don't have anything else to use, and so they continue to use it without worrying about this. And so this is another sort of bug in contemporary theoretical physics, which is largely ignored by the theoretical community.
And does the Schrödinger approach offer you an alternative, or is Heisenberg's approach the only way to possibly even calculate the cosmological constant?
I didn't understand what you said. How do they calculate the cosmological constant?
Well, no, you're saying
The problem is
if
that-
you accept the Heisenberg interpretation and then you calculate the cosmological constant, you get something that's 56 orders of magnitude off from what is observed.
Yes, from
And
what cosmologists will tell you is the real cosmological constant.
Okay, and so the dichotomy that we set up at the beginning was Heisenberg versus Schrödinger. And so is there a way to calculate the cosmological constant using a Schrödinger approach that leads to a better result, or is that just not even applicable?
The Schrödinger approach doesn't. I'm not aware of a calculation based on the Schrödinger approach, but the reason why there's such a big problem with quantum electrodynamics is that there's a thing that was introduced in quantum electrodynamics called second quantization, where you fill the universe with little dipole receptors which sort of absorb and pass along photons which are being sent from one place to another. And that renormalization puts energy in space. I mean, you can't have a dipole present sitting there in empty space without having some energy associated with it. And what as I understand it, what the quantum electrodynamics calculations of the cosmological constant do is they sum up the energy of all of those dipoles that are present because of second quantization, and that's what makes the answer so enormous. And so that says that those dipoles are not really there. And so they have used a trick to do calculations, which is inconsistent with the way the universe really works. I don't know how serious that problem is, but I would, if I were involved in the field, I would worry about it a lot more than I do now.
Well, you guys put the central question pretty clearly at the front of this paper, and you basically point to this problem of a physical interpretation of wave function collapse. What does it mean? It seems like, let me just read from your paper again. You say that the emission and absorption are treated as independent, isolated events without internal structure. It's insisted that the only real and meaningful quantities describing this process are probabilities, since these are measurable. The necessary abrupt change in the quantum wave function of the system when the photon arrives is called the wave function collapse, and is considered to be a mysterious process that the founders of QM found it necessary to, quote, put in by hand without providing any mechanism. The missing mechanism behind the wave function collapse is sometimes called the measurement problem.
Yes.
And so I see, like from where I'm sitting, this is the main thing that you guys are addressing with this transactional interpretation.
Well, we're using the transactional interpretation to see if we can calculate, if we can understand in more detail what wave function collapse really, how it really happens. Whether you can't just wave your hands and say the wave function collapses. You have to describe a process in which it collapses. And this paper that you're referring to, in that paper, we set up something based on the Schrödinger. There's a theorist named Ed Janes who was at Stanford, and then he was at Johns Hopkins, I believe. And he was using the Schrödinger approach to develop an alternative to quantum electrodynamics that he called semi-classical theory or something like that. And it had the advantage that you didn't have to do renormalization because there was no self-energy problem. And the problem with the Schrödinger approach is that it's sort of the don't ask, don't tell approach to quantum mechanics. That you're not supposed to ask what's going on behind the scenes. You're only supposed to focus on the results. Heisenberg had very strong feelings about this because he'd run into problems in the area of trying to understand intermediate results. It turned out to be nonsense, and so he tended to throw all the intermediate results away and only focus on the bottom line. This is fine for doing quick calculations, but it's not very good if you want to understand what's going on behind the scenes. And so, and the Schrödinger approach allows you to do this. And Ed Janes pushed this approach very, very hard and developed some things that turn out to be very useful for understanding systems like lasers. In fact, I guess the development of the laser is due in part to the preliminary theoretical work that Ed Janes did in anticipation of it. But it hits the wall when you come to the question of spin, and when you come to the question of non-locality. It doesn't have any non-locality in it. There was a famous meeting in Rochester where John Clauser, who was the Clauser of the Friedman-Clauser experiment, won the Nobel Prize a couple of years ago, and Ed Janes sort of butted heads, and Clauser presented a result that Janes admitted that he could not explain with with his semi-classical approach to quantum electrodynamics, and the result was that Janes made some sort of a speech in which he said he would be working on it, and apparently he worked on it for a while and gave up, and that's sort of the last major work of Ed Janes that appears in the literature. He bumped his head against non-locality and went down in flames and was, in a sense, never seen or heard of again. What Carver Mead and I found was that you can, if you do a slightly different approach than Ed Janes was using. Ed Janes was using Maxwell's equations for the electrodynamics part of it, and Maxwell's equations came along before relativity, and there's a relativistic approach using four vectors, which is a better way of describing these kinds of wave functions. And what we did was to use essentially the Janes approach, but using four vector potentials. And we allowed there to be retarded potentials, which is what Janes used, and we also added advanced potentials, which is the advanced wave going back and forming the transaction. And we found that when you put the advanced waves and the retarded waves together, you can explain non-locality without any problems at all. That this major roadblock disappears, and if Janes was still around, we could put him back in business.
I was wondering, there's a beautiful figure here that illustrates the basics. Could you switch the screen over so I can show this to people?
Yeah, of course.
This is, I think, helps illustrate what it is we're getting on about here. All right.
Yeah.
So in this figure, what we see, what we traditionally think of is that for a photon to be emitted, it has to be excited to a new energy level, right? Which is kind of what we see over here on the left, I suppose. And then what you're adding to this picture is that there's another atom involved that is also participating from the start of this, we'll call it an emission process, but the emission process, the language of that sort of ignores the fact that there's another atom that's participating from the beginning here.
Yes.
And so this one is actually losing the same quantity of energy, right? It's giving its energy to this other atom in the process. Is that a fair way to think about it?
Yeah, we envision these two atoms not as isolated, not as completely pure objects, but where there is a very, very small submixture. There's the one on the right, the one that has the lower red line, is in its ground state, but it has a small, very small contribution to its wave function from the excited state. And the one on the left, which is in the excited state, has a very small contribution to the ground from the ground state. And these extra contributions produce a beat frequency which generates retarded and advanced waves, which set up this handshake. And it's an unstable situation in which the handshake either rises up and falls down again and nothing happens, or it builds and builds and builds until the energy goes to the other side. And it's not a one-step process, it's a multi-step process where these waves have to go back and forth and back and forth. But since we're doing advanced and retarded waves, it doesn't. There's not a lot of time delay involved in that buildup because part of the time the wave is going backwards in time. So it happens. One of the problems Schrödinger had with Heisenberg's approach to quantum mechanics was that the quantum jumps that Heisenberg was talking about seemed to be nearly instantaneous. They happened really, really fast. And this riled Schrödinger because he thought that that in wave processes, nothing could happen that fast. However, if you're dealing with advanced and retarded waves, the retarded waves go forwards in time and the advanced waves go back in time, and everything happens instantaneously, just as Heisenberg said it should.
I have a really superficial question.
So that was the point that Schrödinger missed because he didn't understand about the advanced waves participating in the process.
Why did you choose to call the wave that comes, the return wave, the advanced wave, as opposed to the retarded wave? Right. So the way that I imagine is that.
I guess because it's moving back in time, or it happens first.
Because the
why does it go back? You're asking why does it go back in time?
No, I'm asking. This is a nomenclature.
It's a mathematical thing, but okay, go ahead.
This is a nomenclature question. So the wave that comes from the first atom, which is the excited atom, you call the retarded wave.
Yep.
And the wave that comes
takes
from
a certain amount of time to go over to the other one, yes.
Sure. And then the second atom that's in the ground state is sending out the advanced wave.
Right.
Why did you choose
a negative amount of time to go back, and so it arrives at the first atom at the same time that it's emitting its initial wave.
I see. And so it's the nomenclature is advanced wave because it arrives at the same time. It's confusing for me because I imagine that the excited it arrives before.
It's very this is the counterintuitive part of the transactional interpretation. How can something arrive before it starts? And the answer is it's going backwards in time. And mathematically, there's an exponential function, e to the I omega t, e to the minus I omega t, which becomes e to the plus I omega t, which means the time delay is negative instead of positive.
And there's also something else that you mentioned in your paper where there is this feature of the radial distribution of the electron function that extends to infinity. And when doing calculations, everybody cuts that part of the distribution off because it's easier to work with.
You're saying you'd have to know the future in order to understand what's going on.
Not even necessarily. I guess I'm just trying to I'm trying to immediately think about the
Yeah,
physical basis for this. Like
there, there's another fundamental physics problem called the arrow of time, as you probably know, and the idea is that effects also have to happen, always have to happen first, and the causes also have to happen, always have to happen first, and the effects always have to happen afterwards. And in other words, time marches forwards and not backwards. And there's a lot of controversy about where the arrow of time comes from. Is it strictly a thermodynamic effect, or is it something more subtle than that? And from my point of view, this is related to this thing about the neutrinos I was talking about earlier. The reason that we have an arrow of time which points forward is that we have a Big Bang reflector in our past, and that reflects things so that everything has to go forward. So if you had a Big Bang in the future as well as the Big Bang in the past, then this wouldn't work. So the one prediction that this idea has is that there is no recollapse of the universe to a sort of a time reverse Big Bang in the future. The universe will continue to expand forever. And modern cosmological information seems to support that kind of effect. That there's no recollapse of the universe. It doesn't expand for a while and then go back down again. It keeps expanding and expanding, expanding, and even accelerating a bit in its expansion according to current theories. So, yeah, the arrow of time problem is an interesting concept, and in my book I devoted a chapter to talking about it. But there's not a lot of general agreement about how you explain it. I have an approach, and other people have approaches, and who knows.
Well, the specific line that I was thinking about in the paper is that you're talking about the envelope functions of the hydrogen atom.
Yeah.
And so you have these two atoms, and you say envelope functions like R1 and R2 generally die out exponentially with distance, sufficiently far from the region of interest, such as an atom. Integrals like this one, and those that follow, in principle extend to infinity, but in practice are taken out far enough that the part being neglected is within the tolerance of the calculation. And my thought as I read this is, I'm like, is it possible that there's something about that portion of the atom that extends to infinity that is playing a role in this transaction? Which, when you're calculating, you can take out because it's negligible, but when we start to think about the physicality of it, there is some portion of it that is not just a mathematical.
This is related to the question of, if you have a wave function that goes all over the place, and part of it precipitates a transaction, what happens to the rest of the wave function? Is it still there, or does it somehow vanish? According to the Heisenberg approach, as soon as an event happens, the wave function that had been moving away goes away, because the wave function represented your lack of knowledge of where the particle was, and as soon as you know where the particle was, you don't need a wave out there telling you that it might have been out there. From the point of view of the transactional interpretation, that's not true. That the wave is a wave and it keeps going forever. And there's a friend of mine named Schroer Afshar, who has recently done an experiment which has only been published as a paper at an APS oral paper at an APS meeting. It hasn't been peer reviewed yet, but he has a setup in which he shows that this sort of dead part of the wave function that's going off in another direction can actually interfere with another wave function that it's indistinguishable from, and produce a change in an interference pattern that is detectable. And so you can actually detect the presence of a so-called ghost wave that was, even after the transaction is formed and is over and done with, that this residual wave is still out there and it can produce interference effects.
So this immediately makes me wonder about the energetics of this, right? Because we tend to look at the photon as being this quantized shift in the energy levels of an atom.
Yeah.
And so if a transaction requires an additional pulse of some motion, some exploratory wave, where does that energy come from if it's not contained in the quantized
As
photon?
I was saying earlier, the usual way of formulating these kinds of things is if you have an atom and it's in some state, and you assume that that state is what is all there is. But in the real world, atoms are continually being bombarded by waves going all over the place, and it's very unlikely that an isolated atom say in its ground state would be purely in the ground state without a little bit of a contribution from the other excited states because of these various the noise of the universe, so to speak. And if you have an atom that's in two states at the same time, which is quantum mechanically fine, that's not a problem. The wave functions from those two states beat against one another and produce a signal, and that's the signal that's making the transactions. And this is sort of spelled out in our paper.
Can I just clarify one thing?
You need that admixture from the non-excited states. That there's a very small contribution to the wave function that's coming from those, and that extra contribution is what makes these propagating signals that can be sent and received and produce the effects.
At the end of the transaction,
as you were saying earlier, in an empty universe, that probably wouldn't happen because there wouldn't be all of this noise that would kick things into other states.
At the end of the so in that diagram that we showed earlier, you have the emitter atom that has all of this energy that it's going to give to the absorber, right? Would we expect that the energy levels will be inverted by the end of the transaction? So the absorber is now...
The transaction has the possibility, it also has the possibility of not doing anything, but it has...
And that's all about the phase relationships? That comes down to phase relationships?
There is, the phase relationships are very important, and as a matter of fact, there could be a lot of atoms in the universe that are participating, but only the one that happens to have a phase relationship that matches the phase relationship of the emitter. The absorber is emitting a wave which has a proper phase relationship with the emitter, and that's what makes the transaction go. And so that's a very important part of the selection process, which is not in my book, but when we did this calculation, Carver and I realized that was really crucial. That's a very important part of the selection process of which atom A decides to send its energy to, because that atom B off in the distance someplace happens to have the right phase relationship to receive it.
This all sounds very musical to me. It's very musical. It's like the atoms are in tune with one another, that are capable.
Of the universe, yeah.
There's something to that, right? There's almost this sympathetic vibration between the two atoms.
Yes, indeed.
Is this used in technological applications where if you're trying to send signals over long distances, that the emitter and the receiver will be more functional if they're somehow forced into this shared phase relationship where they're tuned to each other?
I'm not sure how you'd force them. You would have to know what the phase of atom A was, and then, I mean, in principle, if you had the proper knowledge, I mean, this is usually the problem in physics, that if you knew enough, you could do stuff that you can't. That's impossible because of your lack of information. And yes, if you could tune a distant system to be in phase with the other system, you would greatly increase the probability of receiving energy from it.
Well, basic antenna, basic RC circuit design involves at least tuning frequencies. I mean, that's the fundamental principle, right? Which is you can't be in phase if you don't have the proper frequency, right? So there is some element of that in basic
Yeah,
RC communication.
there are certainly analogies in classical physics and electrical circuit theory and stuff like that, and antenna theory in particular.
And so,
But like, let's stick with the phase thing for a second,
Sure.
because one of the things that I think the phase, and there might be another diagram worth sharing here, because you guys use the phase relationship to express why light travels in a straight line, right?
I guess I would say that light preferably travels in a straight line, but according to Feynman path integrals and so forth, it can also go in various other trajectories as well. The straight line is the shortest distance between two parts, so it's the point, so it's the preferred direction. But
Can I share? Let me share a diagram really quick.
But there were some movies we made, and that I don't know if that.
Can you explain this figure?
That's talking about phase relationships. Those little black lines represent points of where the wave function reaches a certain maximum phase. And if you count the number of black lines that these various paths cross, they all have the same phase when they arrive at the second system, and so therefore they reinforce one another, and that's what helps the transaction to happen. It doesn't have to happen going straight from point A to point B. It can go in the red path or the purple path as well as going straight down the middle.
But the straight down the middle has the highest amplitude with in-phase signals, from what I understand.
Yeah, if you do a measurement of which way it went, you'll always come up with the straight down the middle. But according to the calculations, if there's nothing that's sort of trying to find out which way it went, then it can go in all directions.
And that's really interesting to me. This idea that these atoms need to be tuned, and that the path. The straight path tends to give the most energy. I guess the most efficient transaction is really neat, because it explains why we have this rectilinear motion.
Yeah, and it also explains why you can have an atom in another star, and you can send a signal from Earth, and it will reach that atom when there are so many other atoms everywhere in the universe that it could have gone to.
All right, I have a few more things marked up here.
But it tells you one interesting thing is that when you go out at night and look up at the sky and there's a star, you can see not only did the star 100 years ago send out the light which reached your eye, but your eye is sending out an advanced wave that goes 100 years into the past and encourages that star to shine in your direction.
I've always wondered about, and this is a little far out, but we define the universe by that which we can see. Do you think that that's a fair definition of universe?
Well, I mean, that which we can see and that which we can infer, I guess, is the way I would put it. And the inference is an important part of the process. But yeah, the problem is you're trying to understand the way things work, and some of this is visible and some of it isn't. And so, and the stuff that is not visible, you have to figure out by other methods, logic and mathematics and so forth. But that doesn't mean it's not there.
And I've always wondered, with the idea of light from the stars being a transactional exchange with us here, that creates the visible universe. And then there must be light from those stars and other stars that are interacting with another body of stuff that we can't actually see, because those atoms, those transactions are not coming to us.
Yeah,
and
sure.
So it suggests to me that there's this other part of the universe, which is what you're saying, the part that needs to be inferred, that which cannot be seen, but which is affecting. And that has to do with the separate network of transactions that's happening
Yeah, we
we're
assume
orthogonal
that
to ours.
we assume the same laws of physics work everywhere, even when we can't see them. So,
Yeah. Do you think that that's a fair assumption?
yeah, that's a fair question. But I mean, at some point you use Occam's razor. You try not to to conjure up too many things that there's no way of knowing about.
That's definitely true. Did you find what you were looking for?
Oh, no. I can get more into the paper in a second. I did want to just ask you about this backwards in time business. Would it be an equally valid interpretation that the atom that's at a distance is somehow in contact with the atom that it's networking with from the beginning, and therefore you just have a classical system where both atoms are participating in this kind of coupled resonator system?
I suppose you could look at it that way. I'm not sure what you gain by it, but the that implies a certain kind of communication, which is hard to understand exactly how it could be implemented.
I can tell you, I can break it down a little bit further, maybe why I think that might be a reasonable interpretation. And it comes down to the radial distribution function that Anastasia brought up earlier, which tells us the location of it tells us the charge density and where we would expect to find, let's say, the electron at any given moment, right?
Yeah.
Well, what Anastasia was pointing to is the traditional electron shells of chemistry sort of ignore the small tail of the distribution function.
Yes.
But in reality, we understand that distribution tail does go off more or less indefinitely. Of course, it's becoming exponentially rarer, is one way to think of it. But it does imply that there's some, if we treat the outer surface of the atom, if we treat the atom as a material object, as if it's an actual body that has, the same properties as any other body that we would think of, then the outer surface is the electron. It's some sort of material in motion. And it seems like that material extends almost indefinitely, although in a rarefied fashion, which does give you an avenue to connect atoms to each other.
Ways of connecting it, but the strength of it is infinitesimally small. And so how it can have a dramatic effect starting from a very small value, you have to have a mechanism for some kind of buildup or something like that. In a certain sense, that's what the transactional interpretation does. It characterizes that kind of buildup. You start with very small exchanges of waves that build up to a full-blown transaction, sending energy across space-time. And the reason why it doesn't take a lot of time for that buildup is because you're using advanced waves, and so there's no time delay involved. In my original paper about the transactional interpretation, I described something called pseudo time, which is what you would see if you were making a movie of it, and you watch one thing and another and another and another as they build up. But since they all happen at the same time, all you see is a superposition of that, and so you just see the energy disappear over here and appear over here. But that's an example where you have start with very weak processes and end up with something quite finite and observable.
Yeah, I think that the idea of going backwards in time it stretches the imagination. It seems like physics is the only discipline where you're allowed to do that kind of thing.
Yeah, as you may know, I spent several years on an experiment where I was trying to demonstrate the possibility of non-local communication. The idea that if you have two entangled photons, doing something to photon A can produce a change in photon B, which can be observable, so you can use it to send a signal. There are theorems in quantum mechanics saying that that's not possible, but it's not. The theorems are somewhat ambiguous, and the question was, well, there might be sort of loopholes, like they describe what happens for one particular event, but they don't describe what happens if you have an ensemble of events and you take some kind of average or something like that. So I was persuaded to do an experiment in the basement of the physics building, where the setup was that you had a source of entangled photons that produced two photons that went off in back to back in opposite directions. And there were experiments showing that if you did a certain kind of measurement on the photon going to the right, that you could cause an interference pattern to be either present or absent on the in the photons going to the left. So if you built up an ensemble of many photons, and you did one kind of measurement, you would see an interference pattern, and if you did a different kind of measurement, you would see no interference pattern. The interference pattern in question was whether it bounced off a mirror and went into detector A, or whether it went straight through the mirror and went to detector B. And so it was a sort of a binary thing where you got one or the other. Anyway, what I found was that yes, nature is doing that, but that if you want to do it, but it's not useful for doing communication, because what switches the interference pattern on and off is doing a measurement. And when you measure something, you have outcomes that are, you have more than one outcome. Let's say you have two outcomes, and you either measure outcome A or outcome B. And it turns out that outcome A was consistent with a wave function with interference pattern that looked like this, and outcome B was consistent with a wave function interference pattern that looked like this. And when you put the two together,
they sort of overlay each other.
No interference pattern at all. And so, and since you didn't know what the outcome of an experiment on arm A was, the observer at arm B didn't know what was being measured, and so what he saw was a superposition of these two that has no signal in it. So nature is busily sending it, and this is an important experiment, because in principle you could do the measurement a year later than you did look for the interference pattern, so you could send it information back in time by a year, and because that's the way quantum interference work and entanglement work. But in practice, nature very carefully covers her tracks so that she's doing all of these back in time and faster than light things, but she doesn't allow you to get on the act. And that's what we concluded from when we finally ended up analyzing our experiment with the right mathematics.
And the reason that you say that it's impossible in my book. The reason that you say that it's impossible to determine is because the measurement doesn't produce a distinct interference pattern. It just washes out the previous one into looking like there isn't one at all. Two possibilities for the measurement. Each of those produces an interference pattern, but the two interference patterns are complementary, and when you superimpose the two, there's no interference pattern at all.
It's really interesting. So go ahead.
No, go ahead. Well, I was going to take us into this idea, the Clauser experiments.
Go for it.
Okay, so you talk about quantum non-locality and this collection of experiments that you bin under the umbrella of tests of Bell's inequality and or these EPR experiments.
Yeah.
And you say that every time that the experiment and its analysis have been repeated, there's always the same outcome. There's a definitive violation of Bell's inequalities. Local causal theories are dead. And then you go on to say that much of the literature on violations of Bell's inequalities in EPR experiments has unfortunately emphasized the reputation of local hidden variable theories. In our view, this is a regrettable historical accident attributable to Bell. Non-local hidden variable theories have been shown to be compatible with EPR results. It is locality that has been refuted. Entangled systems exhibit correlations that can only be accommodated by quantum non-locality. The transactional interpretation supplies the mechanism for that non-locality.
Yes.
So let's take that apart. Maybe we can start with this idea of the tests of Bell's inequality, the Clauser experiment that got the Nobel Prize, and then the way that transactional interpretation allows us to see the Clauser results in a different light.
Okay, well, let me start by saying what entanglement involves. The entanglement sort of was an invention, or it was first pointed out by Einstein and Rosen in their criticism of quantum mechanics. They pointed out that if you have a situation where you have particles splitting into two, a system splitting into two particles, each of which can carry a certain momentum away. According to quantum mechanics, you don't know anything about momentum, and so how can it be conserved? And they pointed out that somehow when you measure the momentum of particle B, which had been uncertain up to then, and you know what it is, you instantaneously know the momentum of particle A because because conservation laws still have to work. In other words, in the presence of the uncertainty principle, it's a problem how you preserve the laws of conservation of energy, conservation of momentum, conservation of angular momentum. How do those things continue to work when energy and momentum are both quantities that are subject to the uncertainty principle? And the answer is, if you have two systems that have to conserve energy and obey the laws of quantum mechanics at the same time, the only way you can implement that those conservation laws is if there's a connection between them that does the enforcement so that energy and momentum are always conserved. And all of these experiments that are talked about in my book and various other places about non-locality and entanglement and so forth are basically representations of quantum mechanics and the and conservation laws interacting in such a way as to keep things honest and to always preserve conservation of energy and conservation of momentum. In the case of the Einstein the Friedmann-Clauser experiment, you have two photons that are in a certain polarization state. The reason polarization is relevant is because it's related to angular momentum, and angular momentum is a conserved quantity. So there are constraints on polarizations that they have to match in certain ways in order to preserve angular momentum. And so the two photons go out and are measured over here and over here. And the question is, how do the polarizations of these two end up so perfectly correlated when they're separated in space-time and the measurements don't have anything to do with one another? And this is the sort of essence of the Friedmann-Clauser experiment. They measure these polarizations, and the polarizations are just the same as if you were measuring having one polarimeter behind the other rather than having measuring different entangled photons. You can cross-polarize them and make the counting rate go to zero. You can cross-polarize these two things out at the ends of the line and have the counting rate go to zero just as well. And that was the thing that Jaynes was completely boggled by. He couldn't figure out a way of making that counting rate go to zero. And the answer is that these things are not just receiving the photons, they're sending back an advanced wave back to the source saying, hey, I measured this, and the other says, hey, I measured that. And unless those two things happen or match, then the transaction doesn't happen, and so it can't proceed. And so you have the sort of a V-shaped diagram that looks like this. There it is. You have a V-shaped diagram that looks like that, with the source here and the two measurements on the two ends, and those are and that's the sort of two-way handshake that makes the Einstein-Podolsky-Rosen paradox experiments work. That angular momentum is being conserved, the conservation of angular momentum is being enforced by these advanced waves going backwards to the source and telling it what it's allowed to emit and what it's not allowed to emit. Does that answer your question? I'm not sure whether I got it all, but
yeah, I mean, so the question that I have is that, so you say that when you turn these polarizers at 90 degrees to each other, you can get the incidence rate to fall to zero, and so it appears
that stops the counting rate. And if the two emissions were independent, you could reduce the counting rate that way, but you could never make it go to zero. And so the essence of the Friedmann-Clauser experiment was that there are situations where you can make the counting rate go absolutely to zero by having cross polarizers. And classical, and Ed James's semi-classical theory was not able to reproduce that result, but Carver Mead and I have no problem doing it.
And so what is it about the rotation of because you rotate one polarizer in the Clauser experiment, and then it falls to zero, because that's what it would look like if the polarizers were one behind the other, right?
Yeah.
Okay. So what is it about the rotation of the one polarizer what is the information that's communicated from
what
the
a polarizer does is to pass an electromagnetic wave where the electric vector is oscillating in a certain direction. If I have a horizontal polarizer, the electric vector is going this way. If I have a vertical polarizer, the electric vector is going that way. If you have cross polarizers, you say one only allows the electric vector oscillating this way, and the other only allows the electric vector going that way. And so that means that nothing can get through, because you can't have both of those at the same time. If you have white, completely unpolarized light, and you go through the first polarizer, what you end up with is horizontal polarization. And then you put the vertical polarizer there, and that stops all the horizontal polarization, so the counting rate goes to zero. This is why polarized sunglasses work, because light bouncing off the road bounces preferentially with the electric vector oscillating parallel to the road. And so if you have sunglasses that only allow light that has vertical polarization, you block the glare from the road, and therefore only the unpolarized light gets into your glasses, not the stuff that's been polarized by bouncing off the highway.
And so is there something about the phase of the polarizer as you turn it that's preventing the communication from happening inside the Clauser experiment?
Well, when you turn it, you're changing what it accepts, okay? That if it's this way, then you accept light oscillating vertically. If you turn it, then you're changing it to oscillate and to pass light this way or this way or this way or this way. And if it has pure vertical polarization, if you had it at 45 degrees, say, then some fraction of it would get by, because some of the light was oscillating in the right direction. But as you turn it to 90 degrees, then none of the light has the right polarization, so none of it gets through.
Sure, but then, I guess this is probably due to my poor understanding of the Freeman-Clauser experiment.
I mean, it's not so much that the thing is rotated as it is that it's crossed, okay? That however you got the polarizers in this position, one of them is looking at vertical light and the other is looking at horizontal light. And those are if light was passing through both of them, one and then the other, it would block it. And if you have a two-way experiment where you have entangled photons here and there, those entangled photons both have to have the same polarization state. And so if you only allow the one on this side to have vertical polarization, only allow the one on this side to have horizontal polarization, then you won't get a transaction, because those cannot be verified back at the source, and so the source cannot emit light that has that property, because it would violate conservation of angular momentum.
And so, okay, this is the perfect setup. So that seems like a really simple and non-mysterious interpretation of the Clauser experiment.
That's what I thought. I thought that when I published the paper, I thought people were going to say, "Oh, the problem's solved," and carry me around on their shoulders. But instead, all I got was 15 different arguments about other ways of looking at quantum mechanics. And so,
why do you think that people are so enamored with the mystery of quantum mechanics? Because this seems...
Or the mysterious interpretations, the more supernatural interpretations?
Yeah, I think
part of the problem is that there's all of these professors who got their tenure by proposing some way of explaining wave-particle duality with some half-baked theory. And they certainly don't want to admit that there's another way of looking at things, because they got their tenure by promoting this particular position. So there's a lot more money to be made, say, and having an opposing position than there is agreeing with another thing. And the trouble with interpretations of quantum mechanics, I mean, usually in physics, we have this lovely situation where if you have two theories, you can go into the laboratory and measure, have them both find a case where both of them make predictions that are inconsistent with one another, and then you can go into the laboratory and measure which one is consistent with the experimental results. The problem is that in the interpretations of quantum mechanics, the quantum mechanics is the thing that makes the predictions, and it makes the same predictions no matter how you interpret it. And so you can't go into the laboratory and test the predictions of an interpretation of quantum mechanics because it doesn't make predictions. It's the quantum mechanics itself that makes the predictions. So this, I guess you can say it projects it from being part of physics to part of philosophy, because in the philosophical world they're very used to that situation. In physics, it's a very alien situation to us, and we don't really know how to deal with it very well.
It seems to me like there's a real strong component of
if you
people.
look at interpretations of quantum mechanics on Wikipedia, you find about 15 or 20 of them, and they don't give much guidance about which one you should pay attention to.
I was going to say, I think people really like the ones that don't make sense because they give them a sense of
wonder.
Wonder, yeah. People like the idea that things don't really operate like our everyday life opens up the possibilities for people of, conquering their own death or transcending this ordinary blasé material reality that we live in.
Heisenberg's observer-created reality is an example of that. People love the idea that an observer can create reality. Similarly, the science fiction writers love the Everett Wheeler interpretation, where you have all of these multiple universes where different things happen, and you can make plots where something in universe A it has some effect on universe B, and so forth. So there's a lot of appeal to theories that might be interesting philosophically, but turn out to have not much to do with quantum mechanics.
Have you ever sat down with Clauser and talked about this?
I beg your pardon?
I said, have you ever had the chance to sit down with John Clauser to talk through the experiment?
Oh, John Clauser, yeah. As a matter of fact, when my first paper on the transactional interpretation was, it turns out he was the referee. I was passing through Berkeley on the way back from someplace in Southern California, and I contacted him, and it turns out he's a sailor, and he was the captain of the Berkeley Sailing Club, and so he opened up the Berkeley Sailing Club for my wife and I, and we sat at the bar drinking free whiskey from the Berkeley Sailing Club while we talked about quantum mechanics. And he told me that he was the referee on my first paper about the transactional interpretation, which is the one it was in Physical Review preceding the one that was published in Reviews of Modern Physics. He liked the transactional interpretation, although he had the same problem that all experimentalists have, that there's no way of testing it to make sure it's right. So
that's fascinating. Yeah, we're hoping to speak.
He was also a rather hostile reviewer of Carver Mead and I's paper, because he was the one who was involved in this confrontation with Ed Janes about Ed Janes' Schrödinger approach to quantum mechanics failing the non-locality test, and he was insistent that what we were doing had the same problem, and that there was no way we could. And so we had to add a section of the paper in which we addressed the Friedman-Clauser experiment and showed that our approach put non-locality into the Schrödinger approach to make Clauser happy, so we could publish the paper. But yeah, he's an interesting guy. I gather he's gotten into a bit of trouble lately by denying global warming or something. So he's not always right.
Yeah, we were trying to get him to come on the show to talk about the Bell's inequality stuff, and he was basically like, "Yeah, I'm really not thinking about that anymore. I'm just thinking about the climate change stuff these days." It's funny because he's probably one of the only scientists that I've looked for that just has their home phone number published on the internet.
You shouldn't have said that.
Yeah, maybe he'll take it down now. But it's really funny because it's just he lives.
We called him up one day.
Yeah, and he was still formulating his global warming ideas, and so we haven't landed that yet. But there's something else from this paper with Carver that I was hoping that we could get to, which is the Hanbury-Brown Twiss effect. And so
say that again.
the Hanbury-Brown Twiss effect.
Yes.
And so
This is something I was involved in when I was doing ultra relativistic heavy ion physics at CERN and Brookhaven, because pi mesons that are made out of energy collisions can be subject to the Hanbury-Brown Twiss effect, and you can use this to measure the size of the fireball that produced them by seeing the interference effects present from Hanbury-Brown Twiss.
And so you open a section. Yeah, let me read a couple of things and then we can go from there. So,
okay.
You open the section 13.1, by saying that it is often said that particles in quantum mechanics travel as waves but arrive as particles. The Hanbury-Brown Twiss effect is an example of this principle. It demonstrates that, in the second-order interference of incoherent wave sources, photons are divisible and are not electromagnetic billiard balls that maintain individual identities.
Yes.
And so that's kind of a counterintuitive way of looking at light, because I think that the conventional understanding is that the photon is in fact an indivisible particle.
Yeah, a little ball of energy that travels through space at the speed of light, yes.
Yeah, and so let's
Which is a bit ironic, I might add, because I believe that the word photon was coined by Gian Lewis, who is sort of the godfather of
photons, yes.
Yeah, exactly. He's kind of the godfather of transactional interpretation.
Right. Yeah, let me first explain what the Hanbury-Brown Twiss effect is. Hanbury-Brown is one guy, and Twiss is another, and they're radio astronomers, and they set up a setup where they had two radio dishes on railroad cars so that they could move them apart and bring them back together again. And they were looking, I think, at Betelgeuse, I don't know, one of the nearby stars. And the idea was that if you looked at the radio waves or radio photons, I guess you would have to characterize them as, that were received by these dishes, depending on their distance, that there should be an interference effect where it falls off like sort of a Gaussian with a certain width. And the width is inversely proportional to the width of the object that's emitting them in the first place. The basic idea is that if you have a photon from one edge of a star and the other edge of a star, and these can produce a click in a detector over here and a click in a detector over here, but because of the relative phasing of the waves, you can work out that the distance between the receivers can tell you how far apart the emitters were. And when you look at this from the point of view of the transactional interpretation, what's happening is you're forming a four-way transaction where you're getting advanced and retarded waves going from one source to both detectors and the other source to both detectors. And the phases have to be just right, so that what you're doing is putting together a photon out of two different contributions at detector A and producing another photon from two different contributions from detector B. And the photons that left the star are not the same photons as the photons that arrived at the detectors. Each detector is detecting sort of half of one photon and half of the other photon. So somehow the photons have split apart in the middle of the transition and reformed into new photons at the other end. And the only sort of constraints are that you have to emit one photon of energy at the sources and receive one photon of energy at the detectors. But if you tried labeling the photons and painting one red and one blue or something like that, it wouldn't work because it's not the same photon arriving at the detector that left the star. They're scrambled up and then reconstituted.
And what does the scrambling? What does the scrambling?
Well, radio astronomers have done the experiment. They've sort of backed off from the Hanbury-Brown Twiss effect because they have decided that there are easier ways of measuring the diameter of stars than doing all this stuff with radio dishes on railroad cars. But at CERN and at Brookhaven, my group in the STAR collaboration and in the NA49 collaboration measured pi mesons, which are charged particles that have spin zero, and so therefore they're Bose-Einstein particles, and they behave the same way as photons in terms of the mathematics of this Hanbury-bound Twitch effect. So they're subject to the same kind of thing. By the way, I gave a paper at this in an APS meeting, and John Clauser came up afterwards and said, "That'll never work." And I said, "We're already doing it." And so he was amazed. But anyway, he we have detectors all over the place, and we measure how far apart the pi mesons are that we detect, and we can detect pi mesons here and here and here and here and here, and so you can see the fall off in the correlation as you separate the two pion detectors, and this tells you what the size of the fireball was that you made by smashing two very heavy atoms together at nearly the speed of light. You make a fireball that looks like something like the first microsecond of the Big Bang, and 1,000 particles come out. And some of these are pi mesons that you can use to characterize the thing. People have also used this with Fermi-Dirac particles, in which instead of there being a peak is a valley, that as you move the detectors closer and closer together, the correlation goes to zero rather than going to twice the value, and that works too, and it allows you to do things in nuclear physics with neutrons, for example, that tell you about the size of the collision and things like that. So yeah, the Hanbury-bound Twist effect is a real thing. It's second order interference, and that it's sort of like interference of cross sections rather than interference of amplitudes, but it's a real phenomenon. It works very well, and in terms of, and it's very hard to understand if you insist that photons are little balls of energy that fly through space. And it also tells you that neither are pions, and pi mesons and neutrons are also not little balls of energy that fly through space. They're waves while they're traveling, and that you can reassemble them in different configurations.
And so, do you think that this fractional photon detection is playing a role in interference patterns as well?
I'm sorry, my watch was getting a phone call. I was distracted. Say again.
So, in the double slit experiment,
Yes.
do you think that this fractional detection of photons is also playing a part, or it's not related at all?
Well, in a double slit experiment, if you insist on photons being little balls of energy, then the little ball of energy has to go through both slits at the same time, and that seems to be a problem. And so it's much easier to conceive of it as a little ball of energy at the source dissolving into waves which travel through the slits at the same time, and then reconstitute on the other side as little particles. In other words, particles, in a sense, don't exist. They only exist as conservation, as size requirements on the size of energies that can be emitted and can be detected. But whenever you travel from point A to point B, you pack your bags and travel like a wave. You don't stay as a particle.
So you've said already that the transactional interpretation suffers from a philosophical problem, that it's not a novel theory. It is simply an interpretation of the theory of quantum mechanics. And so it's this philosophical shell that rests on top of a body of evidence.
Yeah.
Is it possible to use that theoretical shell to make some kind of prediction that would differentiate it from the various more mystical and magical interpretations, or is this?
As I said earlier, there's there's one prediction it makes, which is that the universe never recollapses, but that's not something you can test experimentally right now.
That's going to take a while.
But the other thing is, the way you can sort of criticize transaction interpretations is if you find a place where they seem to be inconsistent with the real world. That as long as they're tracking what's really going on as an interpretation, that's fine. But if they tell you something that's clearly wrong, then that's a problem. Now, from my point of view, this has been a problem for both the Everett Wheeler interpretation and the Heisenberg interpretation from an experiment that was done by Schrödinger Afshar, in which he does a double. There's a thing called the Wheeler delayed choice experiment. I don't know if you know what that is, but basically you you have a situation where you have a two-slit experiment, and then you have a lens which focuses the light from the two slits to a point. And so if you allow that, you have a lens which images the two slits, and so you can put detectors at the images, and if you detect light at image 1, that meant the particle went through the first slit, and if you detected an image 2, that went through the second slit. So you can either decide which slit the thing went through, or you can put a screen in the middle where the light is still spread out over the place, and you can see an interference pattern, and which meant that the light had to go through both slits. And so Wheeler said, you can, so it's sort of like the difference between a particle and a wave. If you measure interference, you're measuring waves, and if you measure positions of detection, you're measuring particles. And Wheeler said, okay, so we have a way, a single experiment with a slit, with a screen that can be either erected or laid down, that will tell us, do particle or wave measurements, and you can choose to either do a particle measurement or a wave measurement, depending on whether the screen's up or down. Now, let's have a graduate student who has really, really fast reaction times, and you allow him, he allows the light to go through the slits before he decides whether to put the slit up or down. Then he can sort of decide whether the light is a particle or a wave after it's already gone through the slits and presumably done one thing or the other. Sure, after, and so this was a sort of a philosophical problem that this is not, people actually done the experiment in the laboratory, not so much with fast graduate students, but with electronics, and demonstrated that what Wheeler was describing actually is real. But what Afshar did was, instead of the screen in the middle, on the screen is an interference pattern where the light goes up and down and up and up and down and up and down and up and down. And in particular, there are minima where there should be no particle, no light visible. And so he put a wire at each minimum, and then he measured the intensity of the lights reaching the two detectors after the lens. And if the light was producing interference before it reached the lens, then these wires shouldn't stop anything, because the light should, because the light had the interference minimum there should be minimum interference between the wires and the light. Whereas if the light was just spreading out all over the place, the wires would stop like 5% of it, and therefore you should see a decrease in the intensity. And what he found was that there was no observable decrease in intensity, that there was no evidence that the wires were stopping anything. And so this implies, and Heisenberg and Bohr and company, and the Copenhagen view is that you can, if you do a particle-like experiment, there's no interference, and if you do an experiment-like thing, there's no way of detecting positions. And Afshar demonstrated that this is a way in which you can demonstrate positions and interference at the same time. You can show that there's interference present, and that there's also particles being detected. And the transactional interpretation is fine with this. This is exactly what should happen. The waves should interfere before they reach the detectors. And the issue is whether you form a transaction with a detector or whether you form a transaction with a screen. But Bohr said you shouldn't expect the interference, and Everett Wheeler interpretation said that the two things should end up in different universes, so there should be no interference. And so both of these have, in a sense, been falsified by the Afshar experiment, as far as I'm concerned. Although most of the physics world who worries about such things does not agree with me. But from my point of view, that experiment is a showstopper, which should be taken as a severe criticism of both of those interpretations of quantum mechanics.
And how does the rest of the physics community refute that?
Well, most of the physics community ignores the interpretations of quantum mechanics altogether because it has no effect on their actual use of quantum mechanics in doing calculations. Carver Mead and I showed how you can use the transactional interpretations to modify the way you do calculations and get better results. But this is a sort of an anomaly. It's not part of the way things are in general in the physics community. So there's only a small subsection of us that worry about interpretations of quantum mechanics at all. And and it's a frustrating business because you can't test things to find out who's right.
Who are your colleagues that are, is anybody other than Carver interested in interpretations of quantum mechanics who's dedicated their careers to that?
I don't quite understand the question. Clauser doesn't really care much about interpretations. Clauser is interested in results, and when he was doing that experiment, he actually was expecting that he would demonstrate that quantum mechanics was wrong, and he was actually told me he was surprised when it turns out that quantum mechanics was non-local, because he didn't believe it was non-local until he showed it he and his graduate students showed it in their tabletop experiment.
I mean, my question was, who else is concerned with interpreting quantum mechanics?
Like, are there other young scientists
there
that
are
are
conferences
working?
which I've never gone to, or I've only gone to a couple of them, where where people who interpret quantum mechanics get together and talk past one another, but there's not any group consensus like there. For cosmology, there's the standard model of cosmology where all the theorists get together and agree on the standard model of how things should work in the universe. And there, in the particle physics, there's a standard model of particle physics where people define what they mean by particles and make predictions, and you can say whether they agree with a result agrees with the standard model or not. In quantum mechanics, there's no such thing. There's no standard interpretation of quantum mechanics because you don't really need an interpretation of quantum mechanics to do the calculations, and so the results only are useful in telling you and helping you explain what's going on in complicated and paradoxical situations. My feeling is that if you can't go into the laboratory and test experiments to see who's right, what you can do is apply the interpretation to as many different paradoxical experiments as possible to see which interpretation explains the weird and paradoxical effects most effectively in the most cases. And from my point of view, the transactional interpretation wins that contest hands down. There's not really much in the way of competition. A lot of the interpretations are focused on wave-particle duality and don't even deal with non-locality, or deal with non-locality and don't worry about anything else. And the transactional interpretation covers all the bases and explains everything as far as I'm concerned. But that's not a universal view of things by any stretch of the imagination.
Are there young scientists that are picking up the torch of the transactional interpretation?
I beg your pardon?
Are there young scientists who are picking up the torch of the transactional interpretation and carrying it forward, or are you and Carver the champions alone?
Okay, I'm not sure how to answer that question. If you look on Wikipedia, the transactional interpretation is listed as one of the interpretations, but it's not exactly featured. In fact, the the game seems to be played by different people with different interpretations dumping on one another. And on Wikipedia, you can go in and change the text if you're clever about doing it. And several times I've had to go in and correct incorrect things that were said about the transactional interpretation on Wikipedia. But it's not so easy to do because they don't like people tooting their own horns. It's fine to dump on somebody else, but you can't promote your own views very directly on Wikipedia. So.
But you don't have like a cohort of young up and coming postdocs or
my colleague Ruth Kastner has books on the interpretation of quantum mechanics. She has taken a somewhat different point of view. She doesn't like the idea of sort of going away from Heisenberg, and so she has adapted the transactional interpretation to quantum field theory and quantum electrodynamics, and she likes to characterize the wave function as existing not in three-dimensional space, but in a higher dimensional space, from which it comes down only after a measurement is made, and in Hilbert space, and so from her point of view, that the wave function is not a real object in physical space; it's an object in Hilbert space that evolves and finally reemerges into regular space. Maybe I'm mischaracterizing her views, but anyway, she has her own view of. We've written papers together, but she has her own view about how non-locality works and about how you interpret the how you interpret quantum electrodynamics and quantum field theory. My feeling is that quantum field theory and quantum electrodynamics are wrong, and therefore I don't need to interpret them. But
we're going to talk to Ruth tomorrow, so that'll be
good.
Interesting. Hey guys, quick interruption. I just want to remind you that we're entirely listener supported. We don't have sponsors. We're not selling anything other than t-shirts, which you should check out down below. They're at cost, so we're not making any money off them, but we would love you to rep the Demystify Psi experience all around the world. So consider that. But do consider coming over to patreon.com/demystifypsi and checking out our community over there. We get together once a week, hang out, chop it up about what to explore on the podcast, and I would love to see you there. So if you have just a couple dollars to spare or a fistful of dollars to spare, consider coming over to patreon.com/demystifypsi, and I'll see you there.
I wonder if we can dig into what is one of our favorite topics, which is, when did physics abandon the physical?
Yeah, that's an interesting question, particularly in this age where the string theory has been going on for 20 years or so without making contact with any kind of experimental testing. And there's a thing in physics. Physics is not immune to fashions and expressions of taste and distaste for various kinds of things. And these fashions change. When I was doing experimental nuclear physics, it seemed as though everybody at one time was measuring something or other, and then the next year they would decide that was old hat, and they would go off and in another sub area and measure something else, and everybody would talk about it at meetings. And then if you waited another year, nobody was talking about that at meetings anymore, and we move on to other things. This happens that's experimental physics, where you're in sort of hard contact with the real world, but you can choose what you want to measure and what you want to emphasize, and that kind of emphasis fluctuates. There's a definite sociology in physics that is hard to escape. And somebody that gets a new and interesting result can cause a sort of stampede in a certain direction. Sometimes the results are wrong. I remember one of my colleagues had evidence for what they thought were super heavy elements embedded in a piece of mineral moissanite that came from Madagascar, and suddenly the whole physics community was struggling to try to get pieces of Madagascar monazite so they could put it in their accelerators and look for super heavy elements. And it turned out the results were wrong. There were no super heavy elements, and a lot of excess pieces of Madagascar moissanite lying around. But anyway, theoretical physics is not exempt from this, and it's perhaps even worse. Einstein demonstrated a certain mathematical elegance to the way he approached physics, and this has gotten transmuted to a certain extent, in that if a theory is sufficiently mathematically elegant, then it must be right, and that's sort of the way it seems to have evolved with string theory, that people in the 1980s thought a little bit about maybe describing particles as little contracted dimensions, compactified dimensions of strings. And this, in 10 or 20 years, caught fire, and suddenly every bright theoretical graduate student in the world was trying to get their PhD having something to do with string theory. And the field has evolved and evolved and evolved, and it finally resulted in a situation which I consider to be sort of a disaster, in which the question is whether the string theories that they're predicting describe our universe or whether they describe some other universe. And it's been demonstrated that almost all of them describe other universes that have a much larger cosmological constant than ours does. And it isn't at all clear that any of them can be constrained to have a cosmological constant which is sufficiently small to match the thing we know about our universe. And so there has been an inconceivably large expenditure of theoretical effort into what seems to be a dead end. And I think I ascribe this to some of the social pathologies of theoretical physics, that people can get deluded into spending such enormous amount of work chasing mathematical elegance to the point where it becomes a reduction to absurdity. But anyway.
But where are the roots of that? Because when we started this project, so we have a parallel project to this podcast, which is called Material Atomics, where we've been well before we found out about you and Carver and these other interpretations of quantum mechanics, we're trying to put a physical interpretation onto the mysteries of quantum mechanics. Onto the mysteries of quantum mechanics. Because we were like, okay, so this stuff is really weird, it's really spooky, what if there's a different interpretation? And we ran into all of the same things that you're describing, which is that we would write about this and then show it to physicists, and physicists are like, this is philosophy, not physics. You show it to philosophers, and philosophers are like, this is physics, not philosophy. And so you fall into the cracks between these two disciplines, where you're just kind of like, well, what's going on?
It's because you can't test it. That's.
But I was always, I personally thought that the place where this started to become less physical was the Michelson-Morley experiment. So there's this idea of a luminiferous ether, which is very physical, right? It's an object, it does stuff, very satisfying. Michelson-Morley does the experiment, shows this impossibly small ether drag. Everybody is happy to discard it, jump onto these more nebulous ideas of just things happening without a mediator.
There are occasional attempts to revive ether theory I've seen, but I never paid much attention to them because I thought that was a lost cause.
But it is the first moment where classical mechanics, let's just say physical objects being responsible for all physical phenomena kind of disappears. And that's a really interesting decision point for a science, to make that, to allow that in. For the first time since the religion and the churches dominated things, all of a sudden you have a science that can be explained without physical mechanics. That's very, very bizarre.
And what was
Yeah, there's also the problem that a lot of the entrenched physicists of the 18th century and the 19th century tend to be stuck in their views, and even when Michelson-Morley or whatever comes along, they're not persuaded that they should change their view of the way things work, because it's worked up to now, and so why change? And so basically, one generation of theory of physicists has to die off, and a new generation has to come along, which is willing to take up the torch and look at new ideas before things can progress.
But what alarms me is that a lot of the people that we find that have alternative explanations for quantum mechanics or alternative interpretations seem to be emeritus professors. They seem to be older. And so this idea that there's a new young guard that's going to come in and replace the existing paradigms doesn't seem to bear out, because there doesn't
I think
appear
you're
to be a
right.
young guard.
I retired in 2010, and I'm an emeritus professor myself. Although when I did this work, it was in the 1980s, and so I wasn't an emeritus professor. I simply, well, I guess offline. I guess I told you about how I sort of came into this. I suddenly had a bright idea in the middle of teaching a physics class, and it took me a while to decide that it wasn't an idea that anybody had publicized before, and it might be completely new. And so I decided to write papers about it. But this is not the kind of physics I was taught to pursue. It's something that sort of cropped up as a sideline, and did not really get me much recognition in my own department in terms of coming up with an interpretation of quantum mechanics. That's not something physicists normally, at least in departments like mine, get rewarded for. So it's something I did in spite of the fact that my colleagues were sort of not so sure they thought it was a good idea.
Can you imagine a case in the future where interpretations do change the way that the world works?
What an interpretation can do is to guide you into testing something that you hadn't thought was necessary to test before, and it fills in the gaps between them that are left by the mathematics that sort of inscrutable, and the existing ideas which maybe don't have the right description. As I was saying, that interpretations are all fine as long as they describe the same physical universe, but you might be able to catch one doing something that doesn't describe the physical universe properly, like the example I was giving with the Copenhagen and the many worlds interpretations. But that's not something that's very easy to do, and it's not something that I don't know whether it's likely or not. We're in an interesting situation at the moment, in both both of our standard models. The standard model of particle physics is always right whenever it's measured, and people keep looking for violations of it. And there are a few hints in the area of mu mesons coming along that maybe muons are behaving in a way that's slightly different from the standard model, and but nobody's quite sure. But what we do know is that the standard model of particle physics has like 27 adjustable parameters that nobody knows how the values of them were established, and there must be some better theory behind it, which sort of tells you how to predict these values that you have to put in by hand in order to make the theory work.
And that's where the interpretation could matter, right? If there is a more rational interpretation that is actually easier for people to understand what's going on, then I can imagine that inspiring a new generation of people to make sense of the existing mathematics, perhaps even technologically to implement it better, because it opens their minds to a different sea of possibilities that they weren't anticipating formerly. It may have been there in the math if you knew where to look, but by having that interpretation, I think you really do bring value to the future promise of what will occur as a result of all of the data we already have.
Yeah, we have an embarrassingly large amount of data these days, most of which can be explained, but not all. And in the world of cosmology, they measure the Hubble constant for right now, and it has one value, and they measure the Hubble constant from the cosmic microwave background, and it has a different value, which is a number of standard deviations separated from it, indicating that something was strange was going on. The universe had more mass or something, and more attraction in the early universe than it does now. And there are theories about mass disappearing from the universe without a trace between the Big Bang and now, but nobody knows what's going on. And there's a crisis in that area. People are worrying about whether dark matter is real or whether it's a kludge that people will put in order to explain things that they can't understand any otherwise, and so forth. So it's very clear that both in particle physics and in cosmology, we need a better theory than we have, but we have no idea where it's going to come from.
And in cosmology, there's a huge assumption that this cosmological constant does reflect the expansion dynamics from the Big Bang to begin with, right? So, I mean, I'm not promoting any particular view here, but I'm saying that if we interpreted those redshift and CMBs in a different way, other than as an expansion, then you might end up with a very different cosmological theory as well.
Yeah, but you have to be faithful to all the things that you can observe. And if you look up dark matter on Wikipedia, there's a nice section where it tells you all the evidence, all from 15 different directions, which can be explained by the presence of dark matter. And there are a lot of new theories where people are trying to explain one or the other of these 15 things with something other than dark matter, but nobody has put it all together again to explain how you could have the universe behaving as we observe it without having dark matter doing a lot of things at the same time.
Well, what's really fascinating is you can have a theory that's very accurate but still wrong. And the one that comes to mind is like the caloric theory of heat, right? The idea that heat's a fluid, the mathematics work out pretty well.
Yeah, sure.
But it's wrong, right? That's what's so funny. The interpretation turns out to be wrong. Yeah. And I think that an argument can be made that by reorienting ourselves to the more useful interpretation, we've been able to do more technologically in terms of designing more efficient engines and so forth.
Yeah, from my point of view, the transactional interpretation is more useful than the others because it explains, you can use it to explain more. But
the dark matter one's tricky because it reminds me of, I don't know whose quote this is, but, give me one miracle and I can explain everything to you, something like that.
Yes. Yeah, there's this famous cartoon where the guy is on the blackboard is saying that it had a bunch of equations, and then it says, and a miracle happens, and then there's a bunch of other equations. And somebody says, I think you need to work more on that third step there.
And it's really interesting because it's only physics that's allowed to have miracles. Like none of, we came up through biophysics and engineering, and there's no miracles allowed. You can't just program a miracle into your chip set, right. Or you can't just have miracles as hypotheses in any other discipline. But for some reason, physics is allowed these things.
And that seems to be the wave function collapses and it's a miracle.
Exactly. It's very, very strange to me.
I mean, I think that biology does have a little bit of a miracle because we've never been able to come up with a satisfying theory for how life emerges on a dead planet.
Yes, I've been worrying a lot about that lately.
And so,
from the point of view, I will be 90 years old in October. And since I retired, I have devoted a lot of my effort to understanding what aging is and how to fix it. And I do senolytics, which means you take certain flavonoids and anti-cancer drugs in a big burst 3 or 4 times a year in order to clear your senescent cells. And I'm a volunteer for a program where they're supposed to refresh your mitochondria so that your little batteries that make your cells run are not running down and dying on the spot and producing all kinds of aging symptoms. So there are many unexplained phenomena behind the evolution of life, and also the question of whether there's intelligent life elsewhere in the galaxy. I don't think there is, but a lot of people do. Um,
Galaxy or universe?
the
You say,
galaxy. I think
but
the universe is so big there has to be intelligent life somewhere, but I don't think it's in that. But in our galaxy, I don't think the chances are that there is, because the Earth is such a special place in terms. I mean, for example, we have a moon which is much bigger than the moons that planets that ordinarily have, because of some accident where a Mars-sized object hit the Earth and part of it went into orbit and formed the moon. The chances of that happening in a random planetary system are very small. And what the moon does is stabilize the seasons. The Earth's axis points off at a certain angle, and if it weren't for the moon, that angle would wander all over the place, and the seasons would change, and parts of the Earth would become hot or cold at random, and it would be much harder for life to exist in an environment like that. But because of the moon and all the angular momentum stored in the moon, it stabilizes the system so that the rotation axis of the Earth always points more or less in the same direction, and so our seasons are predictable and stable.
Do you think that's what happened to Mars? Because Mars is also tilted at an
Mars
angle.
has little moons that have almost no effect on anything.
But it also has a similar tilt to Earth, right?
Hmm?
It also has the same, almost identical tilt to the Earth, right?
Yeah, at the moment, but it probably moves around a lot because Mars is closer to Jupiter, and Jupiter perturbs the hell out of things. So,
Interesting.
when do you undergo the mitochondrial treatment?
when about a year, and probably a year from now, I don't know. There's a lot of fundraising going on at the moment. I don't know what it's gonna. It's not going to be cheap, but I don't have to pay for it because it's an experiment. So, but I will probably have to go to some island in the Caribbean to have it done, because the Food and Drug Administration doesn't believe that aging is a disease that requires treatment, and so uh, it makes things difficult for people who are just trying to deal with anti-aging medicine in this country. But
Where do they get the mitochondria?
what?
Where do
do?
where do they obtain the mitochondria for this transplant?
They basically take it's sort of like liposuction. They take some fat cells out of your belly fat, and they extract the stem cells, and then they have a big brewer that that causes the stem cells to replicate over and over and over again until you have many more of them. And then you extract the mitochondria, and in the process, they do things that, if the mitochondria have DNA damage, which most of them, or many of them do, that you have to understand that mitochondria have their own DNA, which is different from the rest of the body, and that the DNA repair mechanisms that mitochondria have are also different from the rest of the body and not very good. And the only reason it's not more of a problem is that cells have many mitochondria, and mitochondria have many of their DNA plasmids distributed all through the mitochondria. So that it tends to average out, and the damage tends to average away a little bit, but it still gets worse and worse and worse as you age, until it reaches the point where 25% of the mitochondria have bad DNA, and you go downhill very rapidly from there. And so in this reading process, they have a way which I've never been told how it works, because it's a proprietary secret of selecting the mitochondria that have the robust DNA and only reproducing those. And then after they get through, they have a mitochondria, which, if they injected directly into your cells or into your bloodstream, the immune system would take them as viruses and go after them and eat them. But they have a way of encapsulating them in a little lipid bubble so that they can evade the immune system and get into the cells. and they do this slowly, little by little, over a period of a couple of months, and you emerge with restored and with many more robust mitochondria than you had in the beginning.
Are you in the first wave of patients?
Yeah, this has not been done before. It's been
really
done on
fascinating.
rats and mice, but not on people.
It's really cool that it comes from your own body. I didn't realize that. That's really interesting.
Well, like I said, I'll be 90 years old in October, and my feeling is that I don't have a lot to lose if things go wrong, and I have a lot to gain if they go right. So I think it's worth the risk, and so I happily volunteer for something like this. But if I was 20 years younger, I probably wouldn't.
Yeah, I'm gonna mark my calendar. I'm gonna check back with you and see if you're aging in reverse a couple of years from now, because I want to get some of these mitochondria too.
Yeah. Start early. What about you said that you also have been doing these senolytic treatments?
What?
You said you were doing these senolytic treatments?
Yes.
Senolytic treatment.
Okay, yeah, let me explain a little. One of the things that happens as you age is that some of your cells become so damaged that they can't function anymore. These are called senescent cells. And there are many causes for this. Radiation happens, their telomeres get too short,
they just accumulate mutational damage, right?
Mm-hmm.
They just accumulate mutational damage over the course of a life, too.
Yeah,
they just don't work
there are
as well.
mutations that cause them to go wrong. A lot of things can go wrong with the cell. And in principle, when that happens to a cell, it ought to go into a process called apoptosis, which is where it sort of disassembles itself and neatly goes away, and its components get recycled. But what, for some reason, and we don't really understand why, in the human body and in other animals, senescent cells hang around. They stop reproducing. Their cell division is halted by biological processes, but they stay there, sort of retired in place, as they say, and they make stuff called SASP, which is toxic and causes neighboring cells to go senescent as well. And so it has a certain aspects of a chain reaction, and this happens more and more. One of the characteristic systems of aging is inflammation. Your whole body gets sort of inflamed, and the result and the cause of this is mainly the SASP caused by the senescent cells. So at the Mayo Clinic in Minnesota, they bred a species of mice by genetic manipulation, where if the cell went senescent, it would produce a protein called P16, and if the P16 was present, there was an enzyme that was coded into the DNA that would go and would cause the cell to trigger apoptosis, and the cell would go away. And these mice were compared with normal mice, and they turned out to be, they had almost no senescent cells in their bodies. They heal slower, but other than that, they were very robust. They lived longer. They lived healthier lives, and up to the very end, they showed very few symptoms of aging. And so,
why do they heal slower? Why do they heal slower? That's really interesting. Why do they heal slower?
Because the senescent cells are involved in healing, and they form a useful function in healing, but they don't do much otherwise except cause problems. Anyway, the Mayo Clinic discovered that by testing a whole slew of different possible chemicals on human cell cultures, that there were certain chemicals that would cause senescent cells to go into apoptosis and disappear. And two of these are flavonoids that are present in strawberries and peaches and things like that, called FISETIN, fisetin, and quercetin, QUERCETIN. And these, and there's an anti-cancer drug that's used for treating leukemia called dasatinib, which Bristol Myers Squibb gets about $1,000 a pill for. Uh, but you can buy it from India for a lot less than that, which also does similar things. And the these three different drugs, to some extent, affect different cell types. The dasatinib attacks fat cells, and the others deal with other kinds of cells, including the linings of your blood vessels and and cartilage in your joints and stuff like that. A lot of the arthritis is caused by senescent cells building up in your joints. And so anyway, there is a movement, shall we say, an anti-aging movement, where we are not waiting around for the stuff to be tested on humans. It's been tested extensively on animals. But we're taking it ourselves, and every 3 or 4 months, I take on 3 successive days, I take large doses of dasatinib plus quercetin plus fisetin, and I feel terrible, like I have the flu for maybe a day, and then I feel wonderful. Because you're killing a lot of senescent cells. It puts junk in your bloodstream that makes you feel bad, and then you feel great for a while. And I've been doing this for about 3 or 4 years, and I think it's had a beneficial effect on my aging. I think I'm in as good shape as I am now because I've been doing this. But it's not the whole problem. It doesn't solve the whole problem.
That's really interesting. I take quercetin also. I think it has some good anti-inflammatory. It also has a monoamine oxidase inhibitor like effect too, which is quite
But if you
interesting.
take it regularly, it has a different effect than if you take a huge dose. They take 3 grams of it or something all at once, and as a big burst. It's a threshold effect, and it doesn't do much to the senescent cells unless the level in your bloodstream reaches a certain level, and that's one of the things the Mayo Clinic found, that too low a dose has almost no effect, but a dose of a certain size, so many micrograms per kilogram of body weight or something, it is required before you get over the threshold and something interesting happens.
Is that research
You
published
might try
already?
3 days of taking very large doses of fisetin and see whether you can see the effects. I predict that you'll feel lousy for a while and then feel very good.
Is it published research that people can check out at home?
There's a lot of literature from there's a group at Mayo Clinic by I guess the leading professor is Kirkwood. I think it's Kirkwood, or no, it's Kirkland, I think. Yeah. Okay. It's either Kirkwood or Kirkland. I always get confused about that name. But anyway, he is the one. His group has done most of the pioneering work, including these studies of chemicals to find out what's important, and it's published in the literature. But all the work has been done on on animals. There are, I believe, some human trials going on right now, dealing with groups of humans that have certain problems that are associated with senescent cells, but there's no work that's being done. I mean, anti-aging research is hard because you give somebody something that extends their age. How can you tell until they die? And so and so it takes a while. And so I am a part of a group that feels that we don't have time to wait around for the Food and Drug Administration to get out of the way so we can buy these things over the counter. So we're doing what we can, making the best of what's available in terms of the and I think senolytics is really important. I think I can feel the effects of it when I take it, and I think that sort of convinced me that it's really doing something. A lot of these supplement things, you think it might be doing you some good, but you can't really tell. But the fact that it makes you feel very bad and then very good seems to me to be a pretty good indicator that something's going on.
And so I looked it up. It's Kirkland.
Hmm?
It's the guy's name is Kirkland, James Kirkland.
Kirkland, yeah, okay.
I mean, yeah, I started my research career after undergrad in an anti-aging laboratory, and it was a really
Rapamycin?
No, we were looking at a lot of different things. It was there was a lot of resveratrol research. We were basically a basic research laboratory that was looking at the mechanisms. And so what does
Yeah.
senescence actually look like? And there's a lot of collaborations with other groups where they were testing things, and we had this assay that could evaluate on a genetic level whether or not it was actually repairing the DNA damage.
And there's also a lot of snake oil salesmen out there. And
Right, because I mean, you're offering people a massive dream of being able to regenerate lost potential. And so it's very, very easy for that to start to go under the radar of the FDA if people are traveling to other countries. And there's a lot of money to be made because the treatments are expensive, like you said. And so it's a delicate thing. But I wonder, do you have a lifespan that you are aiming for? Do you want to live to be like 500 years old?
I no, I don't have a target. I mean, basically, that's saying when do you want to die, and I don't particularly want to die anytime soon. But I can't say I want to live to 500 years old. That sounds kind of boring. But
But I imagine it will happen.
I mean, someone in the next, I think, 2 or 3 decades is going to
Who knows
escape.
when?
I think, first of all, the anti-aging industry is going to explode because there are better and better techniques being, and I've already invested some money in a couple of companies, who were one of which is doing pioneering epigenetic reprogramming, and the other is developing a certain kind of plasmid which does a better job than these things I was talking about of getting rid of senescent cells. And this company that's going to do the mitochondrial replacement, I'm thinking of investing in it as well. But anyway, the field is kind of on the threshold of exploding, and I think that it's a very interesting time. Well, whether I will live to see it come to full fruition and actually extend human lives significantly is another question, but I'm hoping for the best.
So what would you do with the extra time?
Oh, I don't know. The question is, would I like to go back and do some more physics, or would I like to go into another field, or whatever? And I don't know. If I was suddenly rejuvenated to an equivalent age of say 30 or something, I'd probably go back to graduate school and study some other thing, possibly in molecular biology, because I know a lot about molecular biology these days from reading the literature, but the idea of going into a laboratory. I mean, I'm an experimental physicist. I'm very good with my hands. I'm very good at building equipment. I'm very good at figuring out what's going on when you've got certain kinds of results and how to fix them so that look better and so forth. So I might very well start doing something in that area. There seems to be a crying need for people who are working in that area right now, and it looks like a field that's exploding more or less the way nuclear physics was exploding when I was a graduate student.
And that could be a way that people beat the 500-year boredom. They could have multiple lifetimes of full expertise, and then
There's been some works of science fiction that have addressed this kind of issue, and usually it involves if people are rejuvenated, then they start doing something different from what they were doing before they were rejuvenated, and I think that's a very reasonable thing that might happen if you're sufficiently with it to being able to do good things in one area. You probably can do good things in another area.
Are you tempted to write a science fiction book on the subject? I know you've already written, 2 or 3?
I've written 3 science fiction novels. Twister was my first one, which is set at the University of Washington, and in a condensed matter physics laboratory where they're doing something which accidentally changes normal matter into shadow matter and shadow matter into normal matter, and the protagonist and 2 children are transported to a shadow matter version of the Earth and end up inside of a big sphere of their laboratory equipment embedded in the middle of a big tree, and the in our universe, a big ball of wood appears in the laboratory at the University of Washington, and the protagonist in this shadow matter universe and his girlfriend, graduate student at the University of Washington, have to figure out how to get how to reverse the process and get them back. And the other two novels I had are the second novel it's published around 2000, and it's called Einstein's Bridge, and it's set at the superconducting supercollider in Waxahachie, Texas, after the machine goes into operation. And as you may know, it was during the Clinton administration. The project was canceled. It was at the same time they were deciding on funding the super collider and the space station, and they decided to fund the space station and not to fund the super collider for budgetary reasons that were sort of bogus, but killed the project. Anyway, in my novel, the machine was actually built. They were busily doing physics with it. When their collisions produced a certain signal that they were not aware of, which could be detected in other bubble universes, and one of them attracted the attention of a species that was interested in communication and collaboration, who contacted them, and another interested a species that used wormholes to invade other universes and take over their facilities and kill everybody. And so the physics protagonists are warned by this good species that they're treading on dangerous ground because they're sending out signals that can produce very big problems. And sure enough, this comes along, and so the good aliens provide a wormhole that transports two of the physicists back to the middle of the Reagan administration, where they proceed to establish themselves and then manipulate the Reagan, Bush, and Clinton administration in order to get this superconducting supercollider project canceled. And the third novel, which was published about a year ago by Main Books after a lot of trouble because of COVID and one thing or another, is a sequel to Einstein's Bridge called Fermi's Question, in which the humans master wormhole technology themselves and manage to get rid of the alien species that was causing all the problems in the first place.
I like that. But do you think you have another one in you, or are you working on more books?
No, I have not been sufficiently. I mean, it's a lot of trouble to write a science fiction novel, a lot of work, and a lot of intensive effort over a period of years. And I would have to say I have not been sufficiently rewarded for what I've done so far to motivate me to do it again. Because I had a lot of problems with Fermi's Question, because my editor, David Hartwell, I had a contract with David Hartwell and Tom Doherty of Tor Books for writing Fermi's Question and possibly a third book, which got compressed into the two books got compressed into one. Anyway, David was an avid book collector with a lot of books in the basement, and he was carrying a bookcase up a stairway, and his feet went out from under him, and he fell over backwards and landed on his head and died. And he was a very interactive editor. He was the editor of Twister, that first novel I published. And I got another editor from Tor Books who was not nearly as interactive and sort of standoffish. And I turned in the novel, and he had some questions, and so I wrote more and turned in the whole thing. And then about 6 months after that, he told me, A, that he had been fired by Tor Books because they were moving away from hard science fiction, and B, they were canceling my contract. And so I was projected into a situation right at the beginning of the COVID crisis where where I had to find another publisher, and it took me a long time to do it, and didn't work out very satisfactorily. So anyway, so for the moment, I'm done writing hard science fiction. Maybe if I get rejuvenated, I'll write more science fiction novels too.
I like that.
I hope so.
Yeah, I mean, we should catch up down the line. I'd love to hear about how the treatment goes and what you're thinking about in terms of molecular biology. And in the meantime, we'll continue our explorations with other folks that are studying the transactional interpretation, and hopefully we can bring some new ideas to you as well down the line.
One of the things we haven't talked about, which maybe when we had that informal session the other day, I was telling you how I came upon the transactional interpretation. Should I tell you that again?
Yeah, that would be a good anecdote to close with. Inspiration for those searching.
Okay. Yeah, I was I was a graduate student in the late 1950s at Rice University, and I had a class by a guy named Larry Biedenhorn, who was a very distinguished theorist in electricity and magnetism. And in electricity and magnetism, there's a thing called Maxwell's equations, which can be put together to form an electromagnetic wave equation, which tells you how waves move through space. It's a second-order differential equation. You differentiate with respect to both time and space. And the fact that it's second order means that it has two solutions. And so Larry was working this out on the blackboard, and he wrote down the normal solution, the so-called advanced solution, the so-called retarded solution. And then he wrote down another solution. He said, this is the advanced solution. And then he drew a big X through it. And he said, but we can throw this one away because it violates the causality boundary condition. And I had, as an undergraduate, I had a very good course in differential equations, and I knew about boundary conditions, and causality is not a boundary condition. And I told him that, and I said, you're not allowed to throw that away because of causality. That's a prejudice. It's not a boundary. There's no boundary involved, and it's not a boundary condition. And we argued back and forth for a little while, and he said, see me after class. And so after class, he said, he got out his pencil and paper, and he wrote down Wheeler, Feynman, Reviews of Modern Physics. And he said, go over to the library, look up the 1946 editions of Reviews of Modern Physics. There's a paper in there by Wheeler and Feynman that does what you want, keeps the advanced solution and uses it. And you read the paper and tell me what you think. And so I did what he said, and I read about Wheeler and Feynman, and I thought about it and thought some of their arguments were a little phony, and came back and told him, yeah, I read it, I understand it. It looks like a really hard way of doing electromagnetism, so I guess you're right. And so then I forgot about it for 10 or so years. And then I was teaching a class, I guess it was a junior class in modern physics or something at the University of Washington, where I was going over these various paradoxes of wave-particle duality and non-locality and so forth in quantum mechanics. And I was explaining how, for some mysterious reason, this particle over here knew what this particle over here was doing. And I suddenly realized that using the Wheeler-Feynman approach to electrodynamics, one could explain that. And it sort of popped into my head. And a couple of weeks later, I was discussing the first Friedman-Clauser experiment with one of the postdocs at my laboratory, and he was saying how he was suggesting that this was a really remarkable experiment, and he was wondering whether we could do a nuclear physics experiment involving polarized protons that would demonstrate the same effect. And we talked about it a while and decided it was really hard. And maybe it wasn't worth doing because it was done so well with optics. And then I told him that I understood how non-locality worked, and he said, "Oh, really? How?" And so I drew this diagram, the one you were sort of showing a minute ago with this sort of V-shaped thing, and no, not the diagram you were showing. This one I was showing, but and I explained to him that you're just using advanced waves to do the handshaking, and everything comes out okay. And he said, is that published anywhere? And I said, no, I don't think so. I just thought it up. And he said, well, you better you should publish that if it's not published. So I went to the literature and started looking, and I thought it was surely an obvious idea. There's all these psi stars and quantum mechanics. People, certainly somebody thought those were advanced waves before, but I couldn't find anything. I found a guy that was doing stuff with what was the guy's name? Anyway, there was a French guy who was a student of de Broglie, who had talked about Feynman zigzags, where electrons and positrons go backwards and forwards in time, and so he had sort of said a few things. But anyway, I wrote a couple of peripheral papers on the subject, and then in the mid 80s, I was on sabbatical at the Hahnemeyer Institute in Berlin. This is a time when the wall was up, and there was a lot of tension in Germany at the time, I was using a big detector at their with their Bixie cyclotron, and the guy who was the detector expert was a manic depressive, and he went into a very bad depressive syndrome and went out in the woods and hung himself one night.
Oh, wow.
And we didn't have a detector expert, and none of us could make the detector work. And so I had a lot of time on my hands because our experiment program had reached a sort of a halt, and so I had a lot of time to worry about other things. And so I took up the torch with the transactional interpretation, and spent a lot of time in the library doing literature research and so forth, and wrote this paper, which rather miraculously I was able to publish in Reviews of Modern Physics in 1986, and that was the beginning of it. It took me a long time to write the book that followed up on it, The Quantum Handshake. That wasn't published until 2016, so that was like 30 years between the one thing and the other. But that's how the transactional interpretation came into existence. And
At what point did you run into Carver? Was he working on? Was Carver Mead? Was he working on the same problem independently?
Carver Mead moved to Seattle about 15 years ago, and from Caltech, and he had read the transactional interpretation and liked it, and had used part of it in his work on collective electrodynamics. He has an alternative way of doing electrodynamics, where you start with superconductors and you work your way backwards, sort of in the opposite way of the way one normally approaches electrodynamics, putting great emphasis on collective effects, where lots of particles working together. And he had read and understood the transactional interpretation from my 1986 paper, and incorporated parts of it in his book. And there was this place where he had laid out some preliminary calculations for doing this hydrogen atom excitation thing that we were talking about. And so I was approached by a friend of mine who was the editor for a special edition of the journal Symmetry, which was focusing on quantum mechanics, and he wanted to know whether I would be willing to write a paper about the transactional interpretation for Symmetry. And I said, well, there's this interesting calculation that Carver Mead introduced that I think needs to be followed up with a better calculation, and maybe if I can convince him to do something, we can write the paper. So I contacted him and said, hey, this journal wants this paper, and he said, how long can it be? And I said, as long as you want. And he said, wonderful. and because he had a lot to say, and as you may have gathered by looking at it, so we proceeded. I wrote a preliminary Mathematica program I like to do mathematics with Mathematica because I make a lot of mistakes and Mathematica fixes them. And uh, so I wrote a preliminary Mathematica program for doing this hydrogen thing, and then he improved it, and I improved his, and he improved mine, and we built it up and made movies and diagrams and wonderful pictures, and wrote the paper, and that's how I got involved with Carver. He has a lot of other interests besides this, but this was something we were doing at the time of COVID, and we didn't have much else to do because everything was closed down, and so we were communicating back and forth by internet a lot and sending versions of calculations here and there, and and then we sent in the preliminary version, and then we got this hostile referee report from John Clauser, and which caused us to take on the question of non-locality a lot more explicitly than we had previously, and and which was, it turned out to be a very good thing for the paper that John Clauser had stepped in and caused us to do this, because it certainly clarified my thinking about the transactional interpretation and how it works, so I'm very pleased with that result. I hope other people appreciate it as much as I do, but I really like that paper. I think it's a really pivotal thing that, in principle, could start a whole new approach to theoretical physics. Although whether that will happen or not depends on a lot of things that I have no control over.
Yeah, that's a real triumphant scientific story. That sounds like the best kind of criticism that you could get, is one that helps you improve your own understanding.
Yeah.
But yeah, this has been wonderful. I'm glad we got to meet you. Like I said, we've known Carver for a few years, and I didn't realize how big of a role you had played in this idea, and it's something that's very interesting to us in our own work as well. And yeah, it's been a real privilege to sit down with you. So thanks for giving us your time.
Yeah, well, like I said, it was a sideline. It was not I mean, while I was working, doing various things on the transactional interpretation, I was always also doing a lot of other things, building accelerators and going and learning the ropes at CERN and Brookhaven, and getting into a whole new branch of other kinds of physics, colliding heavy nuclei together and making fireballs that look like the first microsecond of the Big Bang. And so this is not something that is sort of my principal activity, but I think it turns out sometimes you have an idea that turns out to be a very good idea, and I think this is one of them. So,
I mean, it's the best kind of scientific story. It's one that's paired with the experimental ability and also the philosophy that backs it.
yeah, in terms of this business about the dichotomy between Heisenberg and Schrödinger, I had not really appreciated that before Carver Mead sort of rubbed my nose in it. When I was beginning in nuclear physics, I did calculations involving the optical model and the distorted wave Born approximation calculation, where we were able to calculate the results of our scattering experiments and our nuclear reaction experiments. And we used the Schrödinger equation approach exclusively. I never even thought about using Heisenberg's way of doing things. But apparently, nuclear physics was using Schrödinger, but high energy physics had sort of focused exclusively on Heisenberg and gone off in a completely different direction. I hadn't really appreciated that very much until I got involved with Carver, and he sort of laid out this dichotomy in a way that was pretty unmistakable. So, and in particular, I didn't know about this confrontation between Ed Janes and John Clauser at this Rochester meeting, and that strikes me as something you could make a movie of or something. It's sort of like the Bohr-Einstein debates, and but anyway, I have learned a lot by associating myself with Carver Mead, let's say.
Me too.
Indeed. Well, let's meet up again down the line. Let's meet up again down the line. It's been a really fascinating conversation. It's something we spend a lot of time thinking about, and it sounds like you've got a bunch of stuff that you're working on that's in a new direction. And so let's talk again.
Mm-hmm.
It was really wonderful. Thank you so much.
My pleasure.